Before I start, please stop me anyone. Okay, so I'll start with motivation for doing this work, which is trying to understand magnetic fields and transport coefficients in the hot intercluster medium of galaxy clusters. So this gas, which is shown by the pink stuff here, is extremely hot and extremely diffuse, and that gives rise to some interesting properties for the plasma. Like many astrophysical plasmas, this is a turbulent system as well. So you can see this is a turbulent map of your deepest cluster from it's a millimeter study, and the structure of the gas itself is very dynamic. You can see curves and so on. So what injects turbulence into galaxy clusters? We have several mechanisms. You have mergers from galaxies, you have feedback from AGN, and you also have galaxies that fall into the cluster medium. So for some numbers, again, extremely diffuse, very hot into the AGN. And that means that the mean part of this plasma, which is basically the length that a charged particle in this plasma travels before it interacts and scatters off of another charged particle in this gas, it's about 30 kiloparsec, and that's pretty close to some next phase that we are interested for the system, and that makes a lot of difference in how we can model this system. So another important number to study turbulence in gas and plasmas is the Reynolds number, which is just the ratio of the velocity times the length scale divided by the viscosity. And the viscosity that I've written here is the Spitzer viscosity. So that it comes from the transport of momentum in this gas is controlled by Coulomb collisions and scattering. So that goes by temperature from 5/2. And this is an extremely hot plasma, which makes the Spitzer viscosity extremely large. And therefore, the kinetic Reynolds number of the intercluster medium extremely low. And what a low kinetic Reynolds number means is that it's going to start suppressing any kind of turbulence that is injected into this cluster. Okay, and we also have observations of magnetic fields. So this here is from a radiation study of the coma cluster. And we also have a lot of studies on cosmological simulations of galaxy clusters, their evolution, and so on. So this year is a plot from one such study. On top, you have the magnetic field structure, and on the bottom, you have the gas density. This is a cluster which never had any mergers in its evolution, and these two are clusters which recently underwent a merger event. So you can see that the gas density itself is sort of distorted into the merger, and that the magnetic fields are kind of linked to what the gas is. So that's why it's important to understand the magnetic fields, because they can be important to the dynamics of the gas. And these are very large magnetic fields. When I say large, what I mean is the amount of energy in the magnetic fields in the ICM is about the same energy as turbulent kinetic energy. So yeah, very high. But we know that clusters themselves did not start out with such strong magnetic fields. They in fact start out with magnetic fields 10 orders of magnitude or more weaker than what we observe today. Yeah. And this magnetic field in clusters also has some interesting consequences for transport properties and transport of heat and momentum in the ICM. So if you can think of the ICM, and this is a magnetic field line. Now, say you have an ion, a proton, that's going to start gyrating about the magnetic field line. And this is the Larmor radius of the ion's gyration. That is pretty small if you consider that the magnetic field strength is about microgauss in the ICM. And why is that important? That's because this number, which is again much less than 10 kiloparsecs for the ICM, is pretty large compared to the Raman radius of these atoms. So that tells us that the transport of heat, momentum, whatever, is going to be anisotropic when you look at it parallel and perpendicular to these magnetic field lines, because these atoms are so tightly bound to these magnetic fields that perpendicular transport just is extremely difficult compared to a parallel transport. So this is the sort of regime we have in the Islam. And we have also had multiple studies which have tried to measure the viscosity of the ICM. Why is understanding the viscosity of the ICM important? Because it tells us how turbulence is dissipated into heat into the ICM and tells us a lot about the kinematics of system itself. So this here is work that looked at sloshing cold fronts in the ICM. And so the top panel has extremely low viscosity. So as you can see, when the -3 spitzer, and the bottom one has two orders of magnitude larger. What happens when you have that viscosity? You basically smoothen out these structures of these eddies. So in this case, they looked at the presence of Kelvin elements vortices. So over here, you can see when it's slow, you sort of start seeing these eddy-like structures, which means that you have a lower value of viscosity than what you get if the Spitzer value is different. So this one puts it at about 10% of Spitzer. This is a study where they looked at a galaxy that was falling into a cluster, and you can see these kind of eddies again, and the stability, which again tells us that the viscosity is somehow lower than what we expect. And finally, you have these recent observations of density fluctuation, amplitude of density fluctuation, where the important thing to get from this graph is that this is the spectra of the kinetic energy with assume if the Spitzer value is the correct one for clusters. But you can see that the cascade impact lies much further down, about 1% of what you have, and this is another study which combine much more observational data. So clearly from a lot of observations, this viscosity does seem suppressed, and it can have a lot to do with the ICM being extremely magnetized. So again, coming back to magnetic fields, we have these extremely strong fields and megaparsec fields. And the question is, how are these strong magnetic fields produced consistent in galaxy clusters? So if I could do collision systems and magnetohydrodynamics to model galaxy clusters, so NHD is a limit where the neutral path is much less than system length scale that you're interested in, then you can look at the turbulent small scale dynamo. That's a mechanism that converts turbulent kinetic energy into magnetic energy. We can see these from the MHD induction equation or the magnetic field evolution equation. So we have two terms on the right hand side here. This is how turbulence gets coupled into magnetic fields and how turbulence is injected into magnetic fields. And then you have this diffusion term here, which is a sink for magnetic fields. So this is essentially the equation that governs the evolution of magnetic fields. And you have a lot of dynamo parameters for the MHD turbulent dynamo. This is very similar to the kinetic Reynolds number, except you just replace the viscosity by the magnetic diffusion. And there's some critical value for this parameter about which you have amplification of magnetic fields. And this is again a system which has been studied in a lot of astrophysical settings like star formation, galaxy evolution, and so on. So yeah. So if I were to simulate the turbulent dynamo in a controlled periodic box, this is how the dynamo looks. So the blue one is the magnetic field RMS. You have three phases in this mechanism. The first one is a sharp exponential growth. Then you have this transition phase and then the fluid saturates. So if you are looking for a turbulent dynamo, this is what you want. You want a very sharp exponential amplification stage, or the kinematic stage is what you see with this turbulent dynamo. So how about this in plasmas which are not so collisional and therefore not modulable by doing machine simulations? People are started looking at it, but it's pretty easy to work. This is again the magnetic energy as a function of time, and you can see in some cases there's some sort of exponential growth in magnetic energy. So what I looked at was trying to understand the properties of these collisionless turbulent time. So to do this, I did kinetic particle and cell simulations, and this method that I developed is a hybrid kinetic or hybrid particle and cell code. So I'll just walk you through quickly what hybrid particle and cell code does. If you can think of having a computational grid, and this is the grid center, and there are many grid cells, but this is a very simple idea. So you have a computational grid, and you have these particles which are free to move and cross these grid cells. Their velocities can evolve because they interact with electromagnetic fields, and if their velocities change, their positions are changed. That is equation of motion. Once that happens, the charge and current densities on the grid itself changes. So you have to tell the grid that the particles have moved and properties of the particles have changed. So you get these properties of the grid centers. Now, once you have that, you compute the electric field, and that has nothing to do with the particles. It's just all computed on the electric on the grid centers, and you need this rho and j's to compute these things. Once you have the electric field, you do what you always do. You plug it back into the Faraday's law, and you have the evolution for the magnetic field or how the magnetic field is stepped in time. Once you have all that, you have to tell the particles that the electrical magnetic fields have now changed. So you interpolate these back to the particles, and this is a very simple idea for a hybrid code does. And we tested this code that I developed on a bunch of problems, and we finally could through theoretical models. We developed this paper for the code itself. But talking about the difference between doing MHD and hybrid kinetic and kinetic models. So it all depends on what length scales and time scales you care about for the problem at hand. So this is just typical numbers in the Earth's magnetic field. This end is the length scale, this end is the time scale. So for extremely large length scales and relatively large time scales, you can do the fluid approach. You have the monthly equation, the Navier-Stokes, or obviously MHD equations, you use them and you solve. Good. But when you start caring about things that happen on the electron time scales or length scales, which could be the Levi length, the electron gyration, radius, and so on, then we have to start doing kinetic methods to get the physics on these scales. But what if you're somewhere in the middle and you have these ions, so this is the ion inertial length and the ion gyration radius, the gyration time corresponding to the ions. You care about the ions and the dynamics of the ions, but you're much larger than any of these scales. That's where you can do hybrid particle and cell methods because it saves you a lot of time. You don't have to do all this electron physics. But you can ask me, we should all just do everything up to here and we will have all the physics always, all the time. We can't do that because it's extremely expensive to do kinetic methods for these length and time scales that we are interested in. So yeah. So to give a sense of how expensive is computationally expensive, we can do fluid codes on our computers now. It would take 12 hours on a very normal computer these days. But if you were to do something very similar problem with a hybrid kinetic code, this is how much or how many computers that would be. So it's crazy. You have to find 300 friends and ask them to give you their computers and at risk of destroying some of their computers. So this is why we need supercomputers to do these kind of problems. So yep. Okay. Finally, coming to the turbulent dynamo and the turbulent dynamo in weakly-collisional systems. There are a lot of parameters for this problem. The first one is the Mach number. So the properties like how fast the magnetic field grows and where the magnetic field saturates, that can depend on the Mach number. That's just the ratio of the turbulence speeds to the thermal speed of the plasma. The second one is the initial plasma beta. This parameter, the dynamo doesn't care about so much, but it's an important physical parameter, physical parameter because of acid plasma beta, which tells you the relative strength of the magnetic and thermal component of the plasma. And finally, you have the initial magnetization. This is not something you would care about if you did collisional systems, but when the plasma is magnetized, then you start caring about the Lambda radius and how big or small the Lambda radius is compared to the computational field of itself. So the plasma itself looks very different. If you have just number greater than 1, this means that the particle in this itself moves from here to there. It can get a drift, it can get a turbulent kick, and it just moves. It never really sees the magnetic fields because the Lambda radius is just larger than what it expects. But then when it gets magnetized, or the magnetic field is strong enough, you can see it gyrates, gets kicked to another place, gyrates again, moves to another place. Yeah. And finally, we spoke about this one, and the magnetic front numbers, just to be sure. These two numbers and all, these are many parameters which are important for understanding the turbulent dynamo and its properties. So, okay, finally, back to some simulation results that I did. So this is a time evolution plot. This is the Mach number, which is Mach on2, it's subsonic plasma, and this is the evolution of the magnetic energy for a lot of different magnetic numbers of atoms. So for the really large atoms, you can see this very sharp amplification that's happening, and that's what you want to kind of say that okay, this is a turbulent dynamo appearing in the system. What happens when you keep decreasing the RM or increasing the magnetic diffusivity, when you start killing more and more magnetic fields to a point where it's upscaling, and eventually all of this magnetic energy is just dissipated. There's no turbulent dynamo anymore. And the point where this magnetic energy amplification stops, or the RM is just so low that this dynamo is not feasible anymore. This is called the critical RM for this problem. So that seems to be around 100 from this plot. Looking at figures themselves, because these are key numerical simulations, you can see that for higher RM simulations, these blue structures in the middle of the box, these are the magnetic fields, they are much more tangled up. And this is a sign of the magnetic fields being kind of coupled with the hydrogens and the dynamo amplifying these magnetic fields, whereas when RM is pretty low, you don't have any, so there's no dynamo. Right. Yeah. And the RD of the system, I don't know, because I don't control the viscosity. This is a much more harder question to answer. So this is putting all my simulations together. In summary, you have a strong magnetic amplification and the RM is large enough. The critical magnetic resonance number is about 100. Change marginally depending on the region that you care about. But this value is again much lower than what people thought would be for the collisionless turbulent dynamo. This thought to be about 1,000, but about 100, which is really close to what you would expect from a collisional MHD system. this work here. So is it already very close to energy and I'm just doing this and wasting every time? No, because you have things that are unlike energy, which is basically the transport and the anisotropic stuff. So there's no collisions to make the component of thermal pressure. So P curve is the thermal pressure perpendicular to the magnetic field, and the parallel is the component of the thermal pressure parallel to the magnetic field. And these are not equal because there are no collisions to isolate that you would have with potential plasma. So you have this number delta, which is larger than 0. And why is that important? Well, because if you have pressure anisotropy, that sets off a zoo of plasma instabilities. Two of which, if we didn't look at for the ICM, are the firehose instability and the Miller instability. So this is an instability where if you have excess parallel pressure, you have like gains in magnetic fields that can get destabilized. In the Miller instability, if you have particles with excess thermal pressure, they start to break out of the magnetic mirror. And when this stuff does happen, these particles are scattering out of each other. So you can think about something which is an instability very unlike particles colliding off of each other, sort of generating an effective viscosity for this collision or collisionless band. So yes, they are interacting, but they are interacting through magnetic field instabilities. Okay. We tried to look for these in our simulations, and it's very hard to do. But over here, for example, we can see these things of bends in magnetic field, and you have excess parallel pressure, and these are sort of sites that you can have the fire force instability set off. I also worked on understanding these statistical yeah.
And that's a conceptual question because we started off wanting to explain magnetic fields in clusters, which I thought challenges that they are coherent over a megaparsec. These things generate no flux at all. They generate tiny scale magnetic fields that have no net rotation measure. So how do you connect what this does, what a cluster is meant to do?
Yeah, thank you for asking that. I actually have a slide.
But maybe we're we're out of time almost.
Yeah, you have like one.
Okay.
Yeah.
Then I will talk much more about this stuff, except that we did some work on trying to understand how all of this compares to MHD. Yeah, so find your question. All of this is on extremely large scales, right? Hundreds of kiloparsecs and megaparsecs. And all of these simulations, including my work and things that other people have done, are over here at the ion electron gamma radius. And there's an extremely large scale separation in the ICM. We know that over here in this regime, this dynamo is extremely efficient. It can amplify magnetic fields, similar to whatever turbulent kinetic energy. What's much less understood is how all of this energy sort of flows back into the larger scale. These instabilities that I talked about, however, don't have to be on these large scales, in that very weak magnetic fields can sort of magnetize the ICM, and you can have things here, this kind of turbulently cascade down to these scales and have particles that are sort of controlling the viscosity. But yes, I would be very happy if somebody can help address the question that you just asked about connecting all of this with the absolute stuff. Yeah, and finally, we know that from observations, viscosity is extremely suppressed in the ICM by the orders of magnitude, which means that the transport coefficients are anisotropic, and something is contributing to this increased effective, decreased effective viscosity of this ICM. And this can be done by these instabilities, and we've seen this in our kinetic simulations. So yeah, this is so I leave you with this summary. Sorry for talking a bit long.